So we'll use the property of convolution and multiplication in time domain in analyzing what happens to the Fourier transform at the output of an LTI system. So earlier we said that if there is an LTI system, the phasor is nothing but the eigenfunction of the LTI system, that is nothing but the eigenfunction of LTI system's convolution operation. So if we want to convolve any signal with the phasor, we don't even have to do the convolution operation. We can directly say the output is going to be the phasor again with a scaled value. And what is the scaling? It's the eigenvalue, and the eigenvalue is what we denoted by this expression, right? It is basically nothing but the inner product of the phasor with the signal with which we are convolving. Now, if you look into this expression of the eigenvalue, something is very clear, and that is the eigenvalue is nothing but the Fourier transform of the signal with which we want to convolve the phasor. So, if we are convolving a signal with the phasor, then the output is nothing but the phasor scaled by the Fourier transform of the signal. This is exactly nothing but the convolution property which we just studied. We have two signals here, both are in the time domain, and when you convolve them, you get the product of these two, where one is in the time domain, the other one is just a constant which is picked up from the spectrum. So this is not a function, so you need not treat this as a function. So h of j omega is the function, but what are you doing here? We are not plugging in the function as such, but then we are just picking one particular value from the function. Okay, and what is that value? The value of the function at omega is picked up, and then that is just multiplied here, because the spectrum gives the value for all possible values of omega. So the spectrum looks something like this, right? So you have h of j omega like this. Now let us say I am feeding in a phasor of frequency 10 pi. Then I will pick the value of the spectrum at 10 pi, okay, and that will be the eigenvalue here. So the spectrum gives us the set of all eigenvalues of the LTI system. So the spectrum of the LTI system is nothing but the eigenvalues for all possible phasors that can be fed into the input of the LTI system. So this is what we see here. The eigenvalues of an LTI system are in fact nothing but the spectrum of its impulse response. So if you take the impulse response and compute the Fourier transform, then each and every value in that spectrum that you get is nothing but the eigenvalue that you can multiply here. Okay. Now, what is the output of this LTI system for an arbitrary input? So the output of the LTI system for an arbitrary input is x of t convolved with the impulse response h of t, right? In the spectral domain, how does this look like? So the spectrum of the output is in fact now equal to the product of the individual spectrums, where what we are doing is simply multiplying the spectrum of the input with the spectrum of the impulse response. Now I can just find the output in the time domain by taking the inverse Fourier transform of x of j omega and h of j omega. So what this tells us is the output in the spectral domain is simply the product of the input spectrum and the impulse response spectrum. So we saw that earlier, right? So whenever you are multiplying two spectrum, the output will contain only those frequency components that are in the intersection of these two spectrums. So the output of an LTI system can never produce a frequency component that is not present in the input or in the impulse response. So this is the important property of an LTI system with which we will construct filters and other kind of systems and analyze them. Another important thing to note is, earlier we said that we can find the impulse response by feeding in an impulse as the input. But what if we are not able to produce an impulse in real life? Can we find out the LTI system's impulse response through other signals? So Fourier transform actually helps us to do that. What does it tell? So it tells us that the spectrum of the output is the product of the spectrum of the input and the impulse response. From this relationship, I can find out the spectrum of the impulse response as this ratio, that is, the frequency response is the spectrum of the impulse response, right? And basically that is nothing but the ratio of the Fourier transform of the output divided by the Fourier transform of the input. Now, if x of j omega is not equal to 0 for all omega, if we can somehow come up with an x of t such that this is true, that the spectrum does not take the value 0 for any value of the frequency omega, it means all frequency components are present in this, then we can find out the frequency response for all frequency values by this relationship. So, even though the Dirac delta function is practically not feasible to be implemented in a system, we can use any signal and still get the impulse response through this relationship. So, we can feed in arbitrary signals where the free spectrum of the input contains all possible frequencies. If you can feed in such a signal, and from the spectrum of the input and the output, you can compute this ratio which gives the frequency response. And the impulse response can be obtained by simply taking the inverse Fourier transform. So, now we have a very nice elegant technique with which we can find out the frequency response and the impulse response of a system without even feeding in an impulse, but any arbitrary signal will work. Only thing is the arbitrary signal should satisfy this property. Let us check if the impulse actually satisfies this property. What if I feed an impulse? What is the Fourier transform of an impulse? The Fourier transform of an impulse is, what is this? This is basically nothing but, once again from the properties of Dirac delta, you can say that this is e power minus j omega 0, which is 1. This is quite interesting because the Dirac delta is a sharp line like this in the time domain, and the corresponding spectrum is a straight line which is equal to the area of the Dirac delta. The amplitude of the straight line in the spectrum is equal to the area of the Dirac delta, which means this also reinforces our uncertainty principle that we studied earlier. So, when in time domain it is concentrated at one particular point, in the frequency domain it is present everywhere. And when the frequency domain, if it is concentrated at one point, it will be present everywhere in the time domain. So, this signal is very narrow in the time domain, but in the frequency domain it contains all possible frequencies. So, if you can localize in time, you cannot localize in frequency. So, that is what the uncertainty principle in Fourier transform means. So, as you can clearly see here, the Dirac delta signal has all possible frequency components from minus infinity to plus infinity and with the same magnitude 1. So, if you substitute that in this ratio, you see that h of j omega is equal to y of j omega, because x of j omega is equal to 1 for all omega. Therefore, if you feed in an Dirac delta signal as the input to an LTI system, the output is equal to h of j omega, which is the spectrum or which is the frequency response. That's exactly what we saw earlier also. So, this simplifies the analysis of LTI systems. You don't have to worry about generating an impulse, computing an impulse and all those things. You can just use this property where the frequency response is a ratio of the Fourier transform of the output to the Fourier transform of the input. And keep that in mind, the frequency response is defined only for an LTI system. For any system, you can say what is the impulse response by feeding in an impulse and seeing what the output is. But a frequency response makes sense only if it is an LTI system, because first of all, the phasors are eigenfunctions of only LTI systems. Only because of phasors, we are defining this notion of frequency response, which is nothing but the eigenvalue of a particular phasor. So, frequency response gets defined only for LTI systems, whereas impulse response exists for any systems.